Hello, everyone. Before starting, I would really like to thank the organizer of this very nice conference for inviting me and giving me the opportunity to present this work, which is a common work with the EDF, which is the electricity company in France. And this presentation is part of the PhD work of Emmanuel Cattel, who defended last week, by the way. And I'm very happy to present this work because these are very nice people I really like to work with. So what is the context of our motivation? Obviously, when you're operating nuclear power plants or nuclear reactors, you want to make safety assessments with a very high level of precision. And in some cases, you want to have a very fine, detailed analysis of cracks or defects. So to do that, we want to simulate the rupture structures, but we'd like to use physically based models so that we have more insights of what's going on in the material. So that's called micromechanics, and that's why the title of the presentation is From Micromechanics to Structures. This involves very large and very complex simulations, and we want them to be efficient indeed, but also reliable. And that's a task. Here you have an example of a 4-point bending of pipeline section, where in the middle you have a girth well. So we analyzed that a few years ago, but I'm not going to speak about that test. I'm going to describe tests we have been doing on this material, which is coming from Germany and which is used in the German nuclear power plant as a secondary circuit pipes. The composition of the material is fairly usual, with a slightly high sulfur content. So the material is not very modern, some kind of material from the 80s, which was representative of a nuclear reactor operating in Europe. So as you see, there's a ferritic microstructure. And here I gave you just the properties at room temperature. Okay, so what do we do? Want to do micromechanics? We need to start, and that's what we call local approach to fracture. We need to start from actual material observation. And here is an observation of the crack tip after some crack extension. I don't know. Here you have the initial fatigue crack, so there's no damage on both sides, and then the crack will grow. And this is an X-ray tomography of the specimen. So we made a slice inside the CT specimen, and what you have here is the summation of voids over 1 millimeter thickness. You see, it's a quite complex void of damage arrangement around the crack. Not so much damage ahead of the crack, by the way. So based on that, we have to imagine some kind of ideal material. That's part of the micromechanics approach. So in that case, we will describe the material as it is a matrix, but containing relatively coarse particles such as manganese sulfides, titanium nitrides, and oxides. But at a lower scale, and these are the small black dots, just to represent that, at a lower scale, and these are the strengthening particles, you have iron carbides, so that the material is not too soft. And at these two types of particles, there's possibility to create damage. So usually, it's very easy to have debonding from the coarse particles, but ultimately, you may have damage at carbides. And if you go to the usual presentation of ductile fracture, we have material with inclusions, the black dots here, and for me, that's the coarse one. You strain a little bit, we have nucleation, and in these materials very fast. The voids will grow, and ultimately they will coalesce. We all know that, and this will coalesce by internal necking and lead to rupture. Nothing very new here. What can happen is that because of the strengthening particle, there may be a secondary damage mechanism where you have extra damage nucleating at these very fine carbides. But to reach that, damage mechanism, you need to strain the material a lot. Do we see that? Okay, no, sorry. So to describe that, we use the well-known now GTN model, Gerson-Sperger-Middleman model. Indeed, we need to use this model in a finite strain framework. Here we use a logarithmic strain measure. So here we have the usual definition of the Gerson model. Basically, it's a definition of the yield surface where you have the effect of shear stresses, parameter stresses, but also the pressure. And we introduce only one damage variable, so that makes the model relatively simple, which is the actually void volume fraction F. And we describe void growth and void coalescence, and so on. So I will not go into the very details of this model, but that's what we have. So on the damage, the model is able to describe growth, but also nucleation, and that's this small fn in red here, because I'm going to speak about it later on. Okay, so now we have a damage model. And I want to outline that when you have a damage model, then you need to introduce some internal length. We're using continuum damage model. In the first session, in the first evening, we spoke about engineering damage mechanics. You can see this presentation as an attempt to do engineering fracture mechanics. So we need a model with softening. That's what you have here. What I plot here is the true strain on the true stress. So you have elastic behavior hardening and then softening up to failure here. When you do that, you dissipate an energy, WR here, and this energy is actually, when you make the integral, these are megapascal, or you can consider that as joule per cubic meter. When you're doing fracture, what you want is an energy per unit surface. So you need joules per cubic, per square meters. So there's a problem here. With the model we use for damage mechanics, we do not get the right energy, not in terms of number, but just the unity is wrong. So to go from there to there, what you need is a length. So the usual way to do it is to say, I'm going to use a fixed mesh size, and that's very important. Here's an example of the mesh dependence you get if you use this model without any precaution. Here's a simulation of a CT specimen. So that's the plastic behavior, no damage. Here I'm the same model. Huh? I'm using a 200 micron mesh down to an 11 micron mesh. I can do that because it's 2D. And there's no convergence at all because of what I've shown before. Okay, you can say, oh, no big deal. I will consider a fixed mesh size. Sorry. I will consider a fixed mesh size, and that will solve more or less my length problem. Not exactly, because in some cases, you also want to predict crack path. Here are three simulations of a tensile bar where you have necking and failure by cut code. So if I use a regular mesh, which is aligned with the direction of loading, I actually get cut code. Now, if I slightly tilt my initial mesh, let's say by 5 degrees, there's no more cut code, just zigzag. And then if I tilt by 10 degrees, I just have pure code. So depending on how I'm designing the mesh, I will get different crack paths, which is a huge problem if you have very complex situation. So, and in some cases also, you want to use automatic meshing, and you will not be able to tune your crack path if you do that. So if we use a non-local model, we can solve that. There are many non-local approaches that you can find right now. You have integral models, implicit gradient models, micromorphic models, straight gradient plasticity models, phase field models, and maybe some more I forgot or I didn't know about. At some point, you have to make a choice. So in my team, we're working on both implicit gradient model, but also the strain gradient plasticity model. And here, that's the one I'm using. So basically, what we're doing, we have here the yield surface, and we just add an extra hardening term which depends on the gradient of the plasticity. So this will create softening and prevent hardening, sorry, and prevent localization. If you use that kind of model, and that's on the right, you see that whatever the number of elements, I get exactly the same. A number of elements is equivalent to the element size in these. I will get exactly the same stress response, more or less the same crack path with cup cone. We also did the test where we tilt the mesh and we always get the same crack path. We get rid of that mesh dependence. Also, there are different numerical strategies to work with this model. Here, we use a fully coupled implicit algorithm. I would say that maybe the hardest way to do it, because it's implicit, everything is coupled, you solve mechanics and non-local damage variability at the same time. But if we do that, if we get convergence, we know more or less that we get the right solution. So then let's go to the material back. We need an experimental database. So we start from tensile test. We have different kinds of notch bars. And these are nice specimens because they're axisymmetric unless the material is anisotropic. And that's very easy, very fast to run. And we have two crack specimens, an SENT and a CT. The CT is the standard specimen we use in fracture mechanics, but SENT is thought to be much more representative of the loading in a pipe. We also added this specimen in the database, and we did test at 26. Someone online. So we did test in 20 degrees and 100 degrees. Now, once again, when you're doing, you want to do some mechanical analysis, you have to look at the fracture surfaces to make sure that your model makes sense compared to what you see on the fracture surface. So here you have two fracture surfaces, one on a CT specimen, and the other one on an SENT specimen. The magnification is indeed exactly the same. And you see very different features. On the left, CT specimen, you see large dimples that you hardly see. They are more or less indicated by the red arrows, but you hardly see them on the CT specimen. So the mechanism of fracture is somehow different. And we interpret that as the nucleation of secondary dimples on iron carbides. Aha. So to be sure, to really validate that, we did what I was. Okay, I don't know what you did, but it's working. Thanks. So what we did, we sliced CTs on an SENT specimen, 1 millimeter thick, and you can put that in a tomograph. What the technique is called laminography, and you can look at damage at the crack tip. So the first picture, you've already seen it. That's that's the damage you have at the crack tip of a CT specimen. And the one below is the damage you have at the crack tip in the SENT specimen. And you see it's very different. You have much larger voids in the CT, much finer voids in the SENT. Something which is very funny in the SENT is that there's no real damage right ahead of the crack tip. There's something like a fan like that where there is no damage. So we need to model that. Okay. So we had to come up with a specific nucleation law to do that. I must say that we didn't want to do that from the very beginning, because when you're developing models, you want to make calculation. The simpler the model, the better it is, for sure. And we really tried hard not to do what I'm going to show, okay? Because that makes the model more complex. But at the end, we decided we had to do it, okay? So it's basically the problem of nucleation or damage. It's relatively low triaxiality for loader parameter, which are about 0. So there's this approach by Nash and Hutchinson, but which is linking voids, and the void they rotate, they elongate, and ultimately they touch each other and that forms a crack. The problem, why did you use that? Because the length scale is the same as the length scale for the large voids. and we see small voids. So we just used a specific nucleation law. I won't touch it. I don't want to touch it. So we say that when we reach a critical strain, you will start to have carbides breaking and creating damage. Okay, well, that's a good idea. Let's try. No way, we couldn't have a good match between CT and ICNT. We really tried hard. And then we had to introduce a load dependence on the critical strain at which secondary nucleation starts. So if the load parameter is 0, then the critical strain is lower than if the load parameter is close to 1. Okay. So you end up with a very complex model, and then you need to identify all the parameters. The slide is busy because there's a lot of work behind that. So we have many parameters. So we devised a strategy in which we try to fit each set of parameters independently. So first, we can tune hardening based on tensile test on notch bar, because before failure, there's very little damage, and we can assume we can neglect damage. And then we need to tune the growth parameter, the one for the big voids. You see these big voids on notch bars on CT specimen. So what we did, we took the notch bars and we ran something like 1,000 tests, okay, with different growth parameters. And out of these 1,000 simulation, we took the 100 best one, which we used to simulate the CT specimen. And out of that, we took the best set of parameters. Then, since the SCNT, that's the specimen where you have a lot of secondary nucleation, we tune secondary nucleation on the SCNT specimen. Okay, and then at the end, we verify that the tuning is consistent using all the parameters. There's a parameter I didn't mention, that's the internal length. This one. So what we did is a very brute force approach where we repeat the process for different length scale. So we start at 400 because 400 will have very coarse meshes, but no way to fit the parameters in a nice way. So we had to go down to 300. We also tried 200, and that gives more or less the same result. So ultimately, we choose 300 microns for the length scale. In that case, we know that the mesh size must be lower than 1/3 of this length to get convergence. So that implies a mesh size of 100 microns. So there was a lot of fitting, and you have to see the last line. We got a good agreement with laboratory size specimen. No wonder, because all the specimens were in the fitting database. So no surprise. So I'm not going to show you these results because they just match, and I don't have so much time. So you have to trust me on that, but I'm sure you do. Okay, so now, with this model, we can move to what we really wanted to do from the very beginning, is analyze, test on full-size components. So what you have here is a segment of a pipe, which is actually welded to two arms, so that we can do the bending test. We check that the both arms they behave elastically, so it's no problem. At the center of the segment, we are introducing a crack. You see the small crack at the bottom. So we introduce different cracks. It's a long process. You don't need to do EDM, and then you need to do pre-fatigue, and this takes months. Here are the two geometries. So FP1, test FP1 is a through-wall crack, and we'll see the crack propagating in the hoop direction. FP2 and FP3, you have a semi-elliptical crack that will first go through the crack and then grow on both sides. So we did FP1 at 2020 C, while it more or less worked. We did FP2 at 20 C, and we had a little bit of ductile crack propagation. And then I was there. There was a big boom in the room, and there was a bit of fracture. We were really frightened because we did not expect that. So, so we wanted a successful test. So we made another test at 100C, and it worked. It was fully ductile. And I'm mainly going to focus on that test. The notch is equipped with clip gauges. You also have drop potential, and there was also cameras to film everything. I'm actually only going to focus on the clip gauges. Okay, here's the testing device. So it's a 4-point bending test. The maximum load is 5,000 kilonewtons, so that's a heavy beast. You have rollers, and you have an image of the test. Huh? So the total length of the setup, is about 4 meters. Okay, so we need meshes, and in the area where the mesh is, where the crack is going to propagate, you need a lot of fine elements, as you can see. We're using, I didn't mention it, but we use quadratic elements, so that's very expensive. Okay. Here's the FP1 test. The crack path was very complex because it started to propagate. So we have this small triangle that you can see here, and then the crack deviates completely. And this is very hard to model indeed. And we only focus on the initiation, the formation of the triangle, and the beginning of tilting. So here is a comparison with the experiment. So the full experiment is the FP1, is green curves. We have damage-free models, it's just for mesospasticity, plasticity, which is slightly above the experiment. And we have the full model in red. It's not very impressive because it's a huge structure. So the crack is relatively small compared to the structure, so it's very little impact on the global behavior. But if you look at the crack path, these are cuts at different positions along the thickness of the pipe. So the one in the middle is what you have at the very center of the thickness of the pipe. So the crack remains flat, and on both sides it will tilt. So that's why the crack seam appears to deviate from the middle plane. On this kind of crack deviation from the middle plane, you only can obtain that with non-local models. You see also, this is damage indeed. You see that the red damage extended over several elements, so non-local stuff. So now we move to FT3. So first, we really focused on the crack going through the pipe. So the same kind of recording, the same kind of very complex crack path. And we did very sharp unloadings to mark the crack front at different stages of the test. And then here we have the simulation. So here the crack is somehow larger, there's more impact on the global behavior of the pipe. So on the graph, you see the experiment indeed. The red dashed line is damage-free model for spasticity. And the red one is our full model. It's working. And I want to mention that here, there is no way we can tune the parameters on this test. It's really a validation test. Because if it goes, if we cannot predict it, there is no way you can retune. The calculation is so long. And if we have the GTN model without the nucleation, you see we're just in between. So taking into account the secondary nucleation is very important. On the bottom, you have a comparison of the predicted and measured crack extension, and that's quite okay. Indeed, experimentally, crack growth is always slightly irregular. So, some conclusions. So I show you a non-local GTN model. I hope I convinced you that using non-local model can be useful. Okay. We had to introduce, and we were not wanted to do that, a low parameter dependent nucleation law. The model was validated, again, experimental data. That's all what we all do that, but also we can use it to simulate a full structure. Next, we are going to analyze the FP2 test. That's interesting because here we are right in the transitional region where you have first ductile crack extension and then brittle fracture. The main point is that this simulation is fairly large. In the small table here, you have the number of total degrees of freedom. So it's between 1 and 3.5 million degrees of freedom. What is important is the number of elements you break. In the last case, you break up to 10,000 elements. You remove them from the calculation. So that's a lot. And you cannot make a huge time step where you remove 1,000 elements at one time. So it has to be very, very long. You have to make a lot of increments, and each increment is very expensive. So this test with a big computer at EDF, it took 11 days, and we use 48 CPUs, so some kind of big calculation. So that's actually an issue we are trying to tackle right now. Solution could be remeshing. We have some papers about remeshing. It's more or less working in 2D. We are still facing big problems in 3D cases, and that could be very interesting to model crack tilting and crack deviation. And the idea is to keep a fine mesh just where we need it, at the crack tip. Ahead of the crack tip, we don't need it. Where the crack has gone, we don't need it anymore. But that's future work. Okay, thank you.